So yeah, if got a mouse as a student, yeah, definitely. Um, so yeah, I gave you feedback on the assignment, and I'm planning to go through the assignment and talk about some of the more common issues that I saw people running into. But somebody just asked me about the one that says not handling quote L space, etc. correctly. So um, the requirements for getting the answer from the user was that you have to accept exactly an H, L, or C, and anything else should throw an error. And so we talked about this multiple times in class, the fact that it's really hard to do that using just scanf. You need to either use string compare or use scanf in conjunction with checking the length or looking for the new line or something like that. But the requirement is that you need to accept only an H, L, or C followed immediately by an enter. So if you type an H followed by spaces, that should throw a syntax error. And a few people did not catch that, and so I took off a few points for that. Not as many as you know, if you accept the word low or high or something like that. But that's what that was. A good make file is a file that does not generate errors, rebuilds everything selectively, deletes everything selectively when you use the clean option. Um, and so if it was missing any of that, then that did not constitute um, a good make file for that assignment. So go ahead and send me an attendance note, and let me run through PA3 and talk a little about the code itself and about some of the things I saw people run into. And if questions come up along the way, just go ahead and shout those out, and we can go from there. So let me pull up. So let's see. General requirements. So these were from the grading rubric, right? So executable must be named main. I think everybody named their executable correctly, which is great. That never happens, so thank you. With no arguments, it should play the game from 0 to 100. With one argument, it should play from 0 to that argument. With two arguments, it should play between those two arguments. So those were three checks I had. Imperfect error handling and command line inputs. If your argument is not an integer, that should throw an error. So I checked for that. Prints a greeting in the beginning and telling the user the range of numbers. I think everybody had that. Make sure it waits for the user to think of a number and then hit enter. So I don't want it to make a guess until the person has, thought of a number and hit enter. So I checked for that. The prediction function should predict the number of guesses. Almost everybody nailed that perfectly. So good job there. Print out the guess number next to each guess. So that was good. And then the algorithm itself was a bunch of the points. So doing the thing that we went through in class, guess in the middle of high and low. If it's too low, add 1 to guess for the new low. If it's too high, subtract 1 from guess for the new high. A few people swapped the meaning of high and low, so I only took off half points for that. Does not compile. So if your code does not compile, right, typically that's a 0 right away. For this class, right, if your code's throwing a compile error, I'll usually go in and see if there's something easy I can fix. So if it's, missing semicolon or something that should have been commented and wasn't, I'll fix that. I'll take off points for not compiling, but I'll keep trying to grade the assignment. But if after fixing a few things I still can't get it to compile, then that's just something I can't grade. And I want to talk today also about what you can do after you've submitted your code to make sure that you submitted the right thing, to make sure that when I try to run the code, it's going to run the same way it does for you. So we'll play around with that. Cheat detection, right? It should detect as soon as low is bigger than high, and then make file issue. So the make file has to be clean. So let's hop in here. So this was my sample README file that describes this was from last year, describes the game, has the date, has my name, and then a synopsis of the program, a discussion of what it's doing, some other features available, the cheat detection, the 3 ways to invoke the program, and requirements on the arguments, and then how you build it by just saying make, clean, and make, and the executable is called main. So if this was something that I was going to share with the world, right, and I put it up on a GitLab repo or something like that, and somebody downloaded it, they would typically look for a README. And when you go to GitLab, if you have a README file, that's displayed on the same page as the front page of the project. And so it kind of gives the user all the information that they might need.
There's actually a little error right there.
I don't doubt it. What's the error?
Can be run 3 ways: main, main, high, low. Should be main, low, high.
That's correct.
Also, having the hashtags right there, or having the hashtags right there, will that mess up the markdown syntax or whatever?
It might. I haven't looked at this in a Markdown viewer actually, but you might be right. But I put that in there because if you actually type this line exactly, it would still run in Bash because those would just be comments. But yeah, I should probably escape those to not mess up the Markdown language. So let me just show you what Markdown looks like. Let me try to do this without exposing everybody's GitLab repo. So here's a project I was working on over the summer. And it's a regular GitLab repo, but there's a README, right? And that README can contain, images and hyperlinks and formatting and lists and all kinds of stuff. And it's like HTML. You just embed tags inside your file. I don't know if I can do the source right here, but you embed tags inside to say I want to start a list, or I want to change a font, I want to add a hyperlink, that kind of stuff. And so README is a text file, but when you view it through something that displays Markdown formatting, like the front page of your repo on GitLab, it'll interpret some of those embedded marks and use them to create formatting and create a link with clickable images and so on and so forth. So yeah, it is just a plain text file, but so is HTML, right? Every web page that you look at in an older website is plain text, but it's marked. So all right, so that was my README, and then broken into a number of .c files, and there's a make file. So if we look at the make file, it looks something like this. So I went ahead and I used some symbols. I used CC as a symbol for the compiler, right? We're just going to use GCC in this course, but I think I was trying to illustrate something here before. But then C flags is normally blank. If I change this to -G, it will basically do GCC-G on all of these. It links in the GDB support. So by default, this is just doing a plain old GCC. But here's my main program that I want to build. Here are the files that need to be present and up to date. And all I need is the object files. I don't need my .h file, right? Well, I don't have a .h file in here. Down here. I don't need my .h file in order to build my executable out of the objects, right? .h is a source file that's included in whatever file I need to use that contents in. So for example, my main.c will include main.h. My other files don't. So this is how I build the executable, and I need these 4 objects, and these are the descriptions of how to build those 4 objects. So if I want to build predict.o, I need predict.c, and then here's the command for it. And then here's the clean command, right, which sort of gets everything back to its original state, and it just removes the files that are built by the make file. So if I say make, it'll tell me main is up to date. If I want to force it to rebuild, I can say make clean, and now when I say make, it will go ahead and just do that selective compilation. And main.c includes main.h. And main.h is primarily my prototypes. So it's just those 3 functions that I was using. And I chose to split it just into those functions, put everything else in the main program. So I don't need to go through this line by line, but just to kind of give you an idea, right? So main program, we definitely need argc, argv, because, you know, we might have command line arguments. And if argc is 2, then they've run the program with the words main space and some integer, hopefully. So that integer would be an argv bracket 1, so parse it the usual way. And then if it doesn't match exactly one integer, I just call error, which just prints a message. Otherwise, this scanf sets the value of this variable high, right? Now I initialize high and low to be 100 and 0. And so if I don't do this, and I don't do this, and I don't do this, right, low will be 0, high will be 100. That's my default. But if argc is 2, they want to specify the high. Well, this scanf will change the value of high. And if there's a problem, I'm going to exit anyway right here. But if there's no problem, now high is set. If argc is 3, then they said main, low number, high number, and so this scanf will set the low, this scanf will set the high. And then if argc is bigger than 3, that's an error, so kick out. If we make it down to here, we've parsed or decided on a low and high range for the game, either by defaults or by command line arguments. So now we just make sure they're legal. Low cannot be negative, and high cannot be less than or equal to low. So if any of those things happen, we'll print the error message and return. Otherwise, if we get down to here, everything's great. We've got our range of low and high, we're ready to play the game. So I do the intro message, which, you know, just says hello, and then I say think of a number between low and high and hit enter when you're ready. I wait for them to hit enter, and then give them a prediction. I will guess your number in at most %d guesses and use the predict function. This keeps track of the current guess, so the midpoint between high and low. This is the number of the guess, which starts at 1. This is a flag I set when we're done looping. And then this is the whole loop. So same algorithm we talked about in class. Guess goes right in the middle. Print out the guess, ask if it's high, low, or correct. Call getAnswer, which will keep, you know, pinging the user until they type in H, L, or C. GetAnswer returns a character, right? That was in the prototype for it. The reason it returns a character is so that our main program can do something like this, right? Call GetAnswer, save the value you get back from that, and then use that to see what your guess was relative to the correct guess. So if GetAnswer returned H, adjust high. If they returned L, adjust low. Otherwise, we're done. We can just say, hey, let's kick out of the loop. And then do your low-high detection. So if low is bigger than high, something went wrong, and that will also kick us out of the loop. And then when done is not 0, we exit the loop here, and that's all. Thanks for playing, and we're done. An error just prints a usage message. And I think that's the bulk of it. So intro.c is just a few print statements. Predict is just using that logarithm function. So 1 plus high minus low is the range. Take the log of that, base 2, return that value plus 1. And then get answer has a little bit more going on inside because it has to do this looping. So I set it up as an infinite loop. Call fgets to read input from the user, and we've already prompted them for a user outside. Prompted them for an answer. So do fgets, and I did something different here. I removed the last character of the line, and then did a string compare to exactly H, L, or C. What I suggested in class was, don't bother with this, but do a string compare to H backslash N, L backslash N, C backslash N. We're going to play with this kind of thing this week. But multiple ways to do this. But punchline is, if they typed an H, return an H. If they typed an L, return that. If they typed a C, return that. Otherwise, prompt them again. Go back up to the top of the loop. Keep trying. And, one more time, the whole point of this is, all of this behavior is hidden inside just a call to get answer, right? And all I have to do is say something like, answer equals get answer. And it hides all of this, right? So I don't have to look at it when I'm thinking about my main program. And this is something I can develop and debug on its own. Right, and it's just a little, it's like printf or fgets or square root or anything else. It's a function that you can just use to do what you want. So, and a little synopsis of what it does. And yeah, someone pointed out in chat there is a log2 function. It wasn't part of original C, but it's been in the standard for 20 some years now. So you can just do a log2 also. But I like dividing by log2. Either way is good. All right, so that's one view of PA3. I saw a lot of different versions of this that worked great. So whatever gets you there. I don't think I missed any chat. Let me see. All right, other questions?
I have a question.
Yeah.
Can you explain to me how string compare works since I didn't use it in PA3?
String compare is a function that takes two strings and returns 0 if they are equal. So string compare S1, S2 compares two strings and returns an integer less than 0, equal to 0, or greater than 0 if S1 is less than, equal to, or greater than S2. So if you do something like string compare quote cat, comma, quote dog, that's going to be less than 0. If you do eel and dog, that's going to be bigger than 0. If you did dog and dog, that's going to be exactly 0. So if you want to know if two strings are exactly the same, run them through string compare, see if it returns exactly 0. And you can't generally use equal equal for comparing strings. So string compare will actually go through character by character, and if both strings match every character exactly, it'll return a 0. If there's a difference somewhere, it'll return something positive or negative to tell you basically which one comes first alphabetically. Where alphabetical means, according to ASCII ordering.
Okay, so it would just give you the value back depending on the first letter of each string?
Yeah. Depending on the first letter, that's different.
So it's like alphabetical order, I guess.
Basically, yeah. So if you do A, B, C, D, E, and A, B, X, D, E, this would be less than 0. Because, A and B are the same, but this C and this X, well, this one is smaller, so C comes first. So that's negative. And so we can use it more generally if we want to order a set of strings, if we want to alphabetize them, we could use this inside a sort function. But most often we're using this just to compare two strings and see if they're the same. And if you wanted to do this by hand, what do? You have to go through, make sure they have the same number of characters, and then look at each character and make sure that they're exactly the same one by one. And that's what string compare does. It just loops through and looks at each character. All right. A few people have been using gotos in code, and so don't use gotos, right? It's worse than considered poor programming practice. It will really sort of terminate an interview on the spot probably. And it's a little silly. I mean, you can use gotos and not destroy the world, but back in the 80s, people decided like we should never use a goto statement. And there was a book, Gotos Considered Harmful, or something like that. And it was the start of kind of this whole structured programming movement. And this makes a lot of sense, right? To use loops and very controlled flow mechanisms and so on. But when you write assembly language, everything is gotos, right? Most assembly languages don't support if-then statements or for loops or things like that. Some of them do. But at the level of assembly language, you're always doing jumps, right? Branches, gotos. But the idea is that we're probably not manipulating code at that level. We're working at a higher level. So chances are, at a university, if you turn in code with a goto, it would be a 0, like on the spot. So definitely get in the habit of not using those, and stick with, while loops, for loops, if then else's, things like that. Yeah, you really have no choice in most assembly languages. And honestly, there are times when gotos can be really helpful, but we can kind of cheat a little too, right? Inside a loop, there's a break statement which gets you out of a loop. There's a continue statement which jumps back to the beginning of the loop, and so you can kind of do most of the things that you would do with a goto anyway. But there's almost always a way to rewrite something with branches like that into something that's structured. So let's talk about checking submissions. Because a number of people are submitting code, and then when I try to test it, it doesn't compile, or it's missing files, or things like that. And that's just human error, right? We can't expect to completely eliminate that. But what you can do is you can double check what you've uploaded, right? So we're submitting everything through Git. So one thing you can do is something like git clone git at gitlab.com username / and in the name of a repository. I don't remember the names of my repositories off the top of my head. Maybe I do. Maybe I have really slow internet. Yeah, I have really slow internet. So you've uploaded your project to GitLab, right? It's in a repository called CSE224. first thing you do, go into an empty directory. Just go to your home directory and make a junk directory, and then do a git clone. Git at gitlab.com. Make sure you spell it right. Colon your GitLab ID, and then the name of your repo, which for you would be CSE224.git. I'm just going to pick on this one because it's one I happen to remember. And this will create under your current directory, in your case, a subdirectory named CSE224. So you can go into that subdirectory, you can go into your PA3 subdirectory, and you should be able to do make clean, and that should remove any compiled files, and then say make, and that should build your executable, and then you can run your executable. You can say main and do all of the tests that you did when you were writing your program. And if you're missing a file, if you push the wrong version of your code, if you named it something other than PA3, if you had something that you added at the last minute that makes your program not compile right, you will see it at that point, and you can correct it, and you can go back into your real PA3 area, make the changes, git add commit push, and then go back, make a new junk area, clone your repository, right? That's what this is doing, and repeat the process. And that's what I do when I grade your assignments, right? I basically have some automated git clone commands that pull down your repo into a subdirectory in my test account, and then I go into your 224/PA3. I say make clean. I say make, and I start running main. So it's totally within your power to replicate what I'm going to do, and if there's some silly mistake, you forgot to include main.c or something, right? You'll catch it right then. Let's see, a Git question: is it possible to set up a second remote? I would like to have my CSE224 repo, my SLP repo, have private copies of my GitLab account, so I have a second backup. Let's see. I don't know if you can have a second area that you push. I don't know if it's possible to set up two remote origins from one directory, where one would get pushed over to a public space and another to a private. Probably your best bet would be to make a second directory, and you might be able to make symbolic links from that directory to your original, but use a different origin. We're going to play with symlinks today, so that might be a way to do it. PA4 we'll talk about at the end of the week. So probably Friday. All right. Let's talk about inodes. Hey. So, say again?
What are we doing for PA4?
Haven't decided yet, but I'm pretty sure it's going to be a group project and it's going to be bash based. We'll go back to C for the fifth assignment.
Are you gonna assign us groups, or are you gonna let us choose them? Or
I'm going to let you choose groups. You can choose your own group. You can choose whether to work with up to 2 other people or work alone. That's my current plan, at least. Like I say, I haven't actually come up with the assignment yet. So ls-l shows us information about files. There's this first column that we've talked about briefly. If this is a D, this is a directory. If it's a dash, this is just a plain file. And there's this ls-i option. If we put an I in there, we also get this magic number in the beginning, right? And this is called an inode number, right? So inodes are a way to see what the internal ID of a file or directory is. And so basically, there's something, you could think of it as an array. It's more sophisticated, but there's something like an array somewhere in the operating system. And when I want to do something with this file called engine.c, it thinks of it as file number 5131671. And using that number, I can access various information about this file, like where it's stored on the hard drive, and other information like that. That's the piece of information I need to be able to do anything with this file. And each file corresponds to a unique, what we call an inode number. And so let's go into a new directory. So this is the original file with a typo. So if I do an ls-il, here's the inode number of this file. Okay. Now we know that we can copy this file. We can say copy original to new, and now I've got two files. My original file had this inode number. My new file has this different number. And I can come into my new file and I can make changes, like get rid of that typo. And my original file is still unchanged because they're separate files, right? They're completely distinct. But what we can do is we can create what's called a symbolic link. So a symbolic link is a way to create one file that's actually just a reference to another file. So let's say I want two different files that point to the same stuff on disk. Here's what I can do. I can say ln, which is link, -s, which says symbolic link. We'll talk about what that means in a second. The file that currently exists and the file I want to create. And now if I do ls-il, my new file shows up as new arrow original. So this file new is called a link, and this column 1 on the ls is an L instead of a dash. That tells me it's a link. Anytime I talk about this file new, I'm actually talking about this file original. And anything I do to original will effectively be done to new, because they're both pointing to the same spot they're both talking about the same file. So for example, here's what my new file looks like, here's what my original file looks like. If I edit the original file, get rid of the typo and make things uppercase, and I look at new, that changes in new. Right? Why is that? Because new is simply a reference to original. If I rename the original file to be original2, new is still a reference to original, and if I try to cat new, it'll say no such file. If I make a new original file with some junk in it, and then I cat new, it's that file I just created. So this is a link between this file new and this file original, but it's called a symbolic link, right? Because it's simply a reference. This is simply referring to that file. And this is the most common kind of link that we use. And so for example, if I say vi, I'm executing /user/bin/vi. If I look at that, that's actually a link to something called /etc/alternative/vi. And if I look at that, that's actually a link to user bin vim.tiny. So when I say vi, it searches my path for something named vi in one of those directories. It finds this, but it says, oh, that's actually this, and it says, oh, that's actually that. And so this is the command that actually executes when I say vi. Now if I wanted to, change it so that everybody on the system, when they run vi, they run a different program, I could change this or this to be that new program. So symbolic links happen a lot, particularly with things that change over time. For example, when I type Java, maybe I wanted to run the latest version of Java. Well, you know, a few years ago that might have been Java 7, and today it might be Java 12. But instead of having to change my commands and now say Java 12 every time I want to run a Java program, I just set up a different link for Java so that Java points to, you know, Java 12 or whatever. My Java setup is a mess on the system though, so who knows what we'll find. This is pointing to etc alternatives Java, which is pointing to Java 8 OpenJDK. So symbolic links are one type of link. The other type of link that we don't use very often is called a hard link. And hard links work like this. So here's my files. And each of these is a separate file on disk, right? They each have their own inode number. So let me get rid of these files. So if I just do a link, and I say here's the file I want to link to, and here's the new file that I want, guess what? These two files have the exact same inode number. They fundamentally refer to the same stuff on the hard drive. And there's really no distinction between them anymore. So if I cat, you know, original, it's got a bunch of stuff in there. If I cat new, it's got a bunch of stuff. If I go into new and I type something reasonable and I cat original, it's got that new stuff in it. Right? And they're the same physical thing. And one of the problems with this is you cannot make a hard link across different file systems. So, you know, I've got some stuff stored under slash, I've got some stuff under /HDD, I've got some stuff under media.nic. Each physical device, this device has its own file system, its own set of inodes referring to files and so on. I can't share these across different file systems, but I can make a symbolic link that takes a file from here and links it to a file under, say, /HDD. And so usually we don't do hard links much. But the one interesting thing about hard links is when you delete one of these files, it doesn't delete them both. So deleting a file doesn't directly delete the file. It reduces the number of things referring to that stuff on the hard drive. Right now I have two files pointing to whatever area of the hard drive contains this information. If I make another file, right, I've got a newer haha, right, and I've got a total of 3 files referencing this. So if I remove the original file, those 2 other files are still intact, and I can cat either of them, right, and they refer to the same thing. But if I remove the last reference to this stuff on the hard drive, then the file is essentially deleted. And the parts of the drive associated with this inode are released. They're marked as available for use, and some other file could come along and occupy those. So that's a little bit about links and such. So questions about that?
So a hard link is a pointer to a file, whereas your soft link is a reference to the file.
Yes. Yeah, a hard link actually refers to the same area of the hard drive. A symbolic link is just saying, here's the name of the file I want you to use when you try to do something with this file. So it's kind of like a shortcut under Windows. And one of the things links are useful sometimes are like if you have some complex path where things are stored, you can type in the whole path to a file. You can say /home/nic/file/this/that/my good program, right? But I could create in my bin directory a symbolic link to that same file, and then if bin is in my search path, I can just type in the name of the file. I think I have this going in Linux actually. So the assess command that you use for ODPs, which we'll come back to this week, by the way, is user local bin assess. But if you look at that, it's actually just a symbolic link to a file in my home directory, right? And this is the program that you're actually executing when you say assess. But I don't want you to have to say /home/nic assess. So you just say assess. This is in your search path, right? So if you look at $path, those are the directories in which the shell will look for a program. So if you say assess, it checks each of these directories, and when it checks this one, it finds assess. And when it goes to execute it, it says, oh wait, that's a link to this, and so it actually runs this program. And yeah, so you use them for game mod managers. That makes sense too. Why isn't there a standard way to format that data, like overwrite it with all empty data? What data are we talking about? This is a chat question from a few minutes ago. Data you remove. You can remove with an overwrite. I don't know if RM has that option by default, but there's usually a wipe command that you can use or install if it's not there that will actually rewrite the areas of the hard drive where your file was stored before removing it. But yeah, with RM, it might be possible to recover some of the contents, so you can use shred to actually overwrite the file and then delete it. And there's all kinds of science around how to do this. There used to be this thing from DoD called the Orange Book that prescribed different ways to shred a file on disk based on security requirements, and overwriting it with alternating patterns of ones and zeros basically. Because if you just write zeros into a file, it's still possible to recover the original file based on the magnetic polarization of each bit, right? If it was a 1 and you wrote a 0, it will look a little different from if it was a 0 and you wrote a 0. And so if you go into a lab with the drive and you analyze it physically, you can still recover this information. So there's all kinds of different ways to do that. How did you know that? I did work for DoD, but that's not how I know it. I learned that in a computer security course when I was an undergrad. What sort of data recovery would be remotely possible on an SSD? I think SSDs, when you erase them, you're physically damaging a little piece of the substrate, which is why there's a finite but large number of rewrite cycles possible. But I suspect those are Department of Defense.
You work for the Department of Teach?
Briefly, yeah. Well, not briefly, but yeah, I worked at a lab called Naval Research Lab in Washington, D.C. I actually did a co-op there as an undergrad, which was great.
Nice.
What did you do there?
They hired me to do work on radar, and I knew nothing about radar. I had not even taken a fields and waves course yet. But I knew about computers, and so, my first summer there, I wrote code to generate maps of what radar patterns would look like, right, based on the type of antenna and so on. But yeah, I was with Naval Research Lab for about 10 years, and it was an amazing place to work because they had a lot of interesting things going on. There were a few Nobel Prize winners on campus, So, you know, you might go over to the cafeteria and sit down next to someone who's got a Nobel Prize in chemistry, you know, and just be like talking to them about whatever. And that was just kind of a really cool environment to be in as an undergrad, especially when I was trying to figure out what I was interested in and such. But computer security course, you'll learn all about you know, data recovery and hiding data, shredding files, things like that. I suspect it's pretty easy to do on a solid state drive, but I haven't looked at that. But definitely, you know, just erasing a file does not get rid of the information, and to overwrite it, you have to sort of do some very deliberate things to make that happen. All right, cool. That brings us to the end of our class, actually. So I was about to talk about archives and the tar command, but we'll go ahead and we'll talk about that tomorrow. This is just it's kind of like a zip command, but there's a utility called tar that will let you make an archive of a whole directory tree of files, if you like, and will preserve all the information about ownership, creation, time, permission bits, things like that. Go ahead and send me an attendance note, please, and we'll talk about a few more Unix commands tomorrow, and then we'll start digging deeper into strings in C. All right, so have a good one. I will see you next time.
Have a good day.
Good day.
You too.
Good day.
You too.
Good day.
Yeah, questions are always good. You don't have to save them.